I just trying to time it for Laura to get that started on time. Okay, the last day we covered part one of that textbook, which dealt with broadband optical fibers and how to derive the optimum. Remember, we arrived at a C-band for the transmission window for broadband optical fiber. That was the optical fiber there. And we talked about this little laser chip here, which is also only here thick, 100 microns, few hundred microns at most, focusing the light into the optical fiber. Today we want to concentrate on these lasers. How do we get 200 terahertz bandwidth and optimally utilize the semiconductor lasers? So I'm going to actually refer back again to this little experiment with the boron, because in fact the standing waves that we talked about for the optical fiber in this acoustic drum are also applicable, as we see on slide 9 or 8 or something, to quantum well lasers. So remember, there was a fundamental mode, then there was a higher order mode, so there's the higher order mode had an oscillation in a ring out here, and an oscillation in the center, and a node in the middle. We'll find our electron waves do that too. And the fundamental mode is vibrating here, the center, and fading towards the edges, just as our electron waves. So there's a correspondence there with the light in the optical fiber. Now, I'm going to move to discuss these broadband lasers and the materials we need to select to make them work. Here in Ireland, we're lucky to have some fabrication companies such as Analog Devices in Limerick and Intel here in Dublin, manufacturing microprocessors and computer chips. And those companies would dearly love if they could get the silicon, which is the basis of their chips, to emit light. Alas, doesn't work. And we're going to show you why. If they could have used silicon, you see, they could grow a silicon laser on the same chip as the microprocessor and have it speaking to another microprocessor or to an optical fiber or to a communication link or whatever, all monolithically. But it doesn't work because of the band diagram of silicon. It's been necessary to find new materials, and they're listed there, which we call 3-5s. So silicon is in group 4 of the periodic chart. 3-5s comprise of something like, say, gallium arsenic. Gallium is in group 3 and arsenic is group 5. And these materials have a band diagram that does work and will, what we say, luminesce. So let's take a look at the energy band diagram. As a free electron has got an energy, and from your basic physics, it's p squared over 2m, where p is the momentum. So we've got m squared v squared over 2m, that's a half m v squared. So look at that expression. That means the energy against p diagram is a parabola, e to p squared. And that's shown here as a dashed line. Energy against momentum. For an electron, remember, the momentum p is related, according to de Broglie, to the wavelength. It's h Planck's constant over the wavelength. Now, the people who have conventionally studied these crystals, there's a unit cell. The atoms are spaced A in the x direction, B in the y, and C in the z direction. So that's our unit cell. And people who study those in crystallography, instead of using P, conventionally they use wave vector, K. But they're one and the same thing, because the wave vector K is 2 pi over lambda, the constant over lambda, and the momentum is in a different Planck's constant over lambda. So they're one and the same thing. However, it is convenient to actually use K to see what's going on, because when you take the potential in this crystal, it's no longer, we don't no longer have a free electron. We have an electron in a potential that's rising and falling and rising and falling according to the unit cell dimension A. So V of A is equal to V of X plus A, V of X plus 2A, and so on. Keeps repeating. And you put an electron into that electrical environment, the band diagram changes. Now, I've said before that when you read this textbook, all diagrams are drawn as free line diagrams so that you can repeat them. And when you repeat them, you will absorb the information. You'll absorb the units that are on the axis. K is per micron. It's 1 over wavelength. And you'll observe the important numbers like pi over A, 2 pi over A, and so on. When the electron is in that periodic potential, discontinuities occur at pi over A, 2 pi over, and in the minus direction as well. And as you well know, I'm just quickly revising your band theory of semiconductors. This turns out that there are energy gaps which are forbidden. There are energies which are disallowed. But the gaps occur, that's why we use K, they occur at pi over A, at points that we can identify. All right? Now, when you're drawing this yourself freehand, just go to your parabola, draw a parabola as quick best you can, and draw a little S like that, and then leave an energy gap and do another little S gap and another S, and you'll end up with your band diagrams. On the other side, the situation is identical, but it's a mirror image. So that means that you're actually spending energy drawing a mirror image. So why not use the left-hand side, and that's what we do later on, left-hand side for a different direction in the crystal. So you'd have B, pi over B, and pi over 2 pi over B, and so on that side. Right? That would make, since B is different from A in the unit cell dimensions, the discontinuities are slightly differently positioned. Right? So the actual band diagram looks a bit unsymmetrical, but that's only because you're compressing more information into the one diagram. You're putting a different crystal direction on the left-hand side to on the right-hand side. Otherwise, it would look symmetrical all the time. Okay? Now, that's one way of compressing energy in the band diagram. Another way is to recall that, look, at these energy gaps are reasonable up here, but when you get down here, they're so big that it requires X-rays to access them. And that we're not interested in that. In conventional electronics and indeed in photonics, we're only interested in the two upper bands. Right? We call them, as you know, the conduction band and the valence band. Now the next thing, so eventually we'll dispense with all the lower bands. The next thing we do, and Brewan suggested this, that why not, in order to see what's going on, slide all of these S's sideways by 2 pi over A. That's compressing the information even further. And when you do that, this S moves down to here, that S moves up, and you can see you're creating a little basin shape. And that's what we have here. And the next two, you do the same thing and you get an inverted basin. And they're the only bands we care about. The energy gap there, turns out, is just about right for infrared or visible light, depending on the semiconductor you pick. Okay, we call that our compressed or reduced Brewan zone diagram. Now, when an electron finds itself in this upper conduction band, it falls down like throwing marbles into a basin, falls down to the bottommost quantized level, and then makes a transition, and as you know, you'll get an energy emission. The photon of light is equal to that energy gap. And that's what happens in gallium arsenide. The transition is as shown there, it's vertical, which means the photon emission conserves energy, but because it's vertical, it also conserves momentum. There's no change in P, or K if you like. However, you do the same now for silicon, and you'll find that this basin is sideways translated, and the dip is up here. That means the electron has to make a diagonal transition to reach the valence band. Diagonally means there's a change in momentum. You must conserve momentum, so there must be a third particle present to help conserve the equation for conservation of momentum. And we're in a crystal, so the most likely candidate is a vibration of the crystal, which we call a phonon. The particle related to that vibration is a phonon, and it participates along with the photon and the electron, and the three particles could produce light in silicon. However, unfortunately for the silicon manufacturers, the likelihood of a third particle being in exactly the right place at exactly the right time is extremely low. So very, very few photons are emitted from a silicon diode. Now, you can take a silicon diode and strip off the plastic cover and see, put a very sensitive light detector up to it, like a photomultiplier tube. That's a tube with a positive and a negative anode and cathode in it. And if a photon goes through there, it ionizes the gas in there and you get a pulse of current. So a photomultiplier tube can pick up single photons. And you put that device up to your silicon diode and you will get an odd blip out of the photomultiplier tube, but very rarely. If you add up them all, you might find it's less than picowatts, maybe femtowatts. We want, for communications, we need milliwatts. That's 1 billion times higher. Therefore, the candidates we have to settle on is these alloys, like gallium arsenide, indium phosphide, mixes of 3 of these, which is called ternary alloys, ternary 3,5s, and mix of all 4 of them is called a quaternary 3,5 alloy. Okay. Now there's a lot of mixes available with just with those 4 elements of the periodic chart alone. There they are: indium, gallium arsenic, and phosphorus. Let's start simple. Gallium arsenide is a binary compound. You would have to start by growing gallium arsenide and measuring its energy gap. And you would be able to associate then the wavelength associated with it, with that energy. The way you would do it is you take a vacuum chamber. It's a bit like how we grew our optical fiber. In fact, optical fiber technology derived from the semiconductor technology. You would inject gases, carrier gases for gallium and for arsenic, into the vacuum chamber, allow them to react, and deposit a layer of gallium arsenide, and another one, and another one, and another one. While you're doing that, you could also program valves, your computer program, to control all the injection gases, so that a carrier gas for P-type material, like tin, is injected. And you could grow a P layer. And later on, you could knock off that valve and knock on another one, which injects an N-type carrier for doping N-type, like germanium. And we could end up with a layer of P-type and a layer of N-type gallium arsenide. We then take out that wafer out of the vacuum chamber and we'd dice it up. Before we dice it up, we'd have to metallize it to upper and lower layers in order to get electrical current in and out, dice it up into chips, and we'd have a load of gallium arsenide diodes. We'd connect a little hair-thin bond wire to the upper metal and a hair-thin bond wire to the lower metal, and then connect it to the outside electrical world. So that's our aim. But before we do that, the question is, what about these other mixes? Look at this ternary situation down here. We could have a carrier gas bringing amount X of gallium, and another valve opening to allow in amount 1 minus X of indium, and a unit amount of arsenic. Those quantities are the mole fractions. When you're cooking, you use spoonfuls or grams or whatever. In bandgap engineering, you use moles. A mole, as you know, is 6 by 10 to the 23 molecules. Okay? So if you took conventional gallium arsenide that you'd already tried to grow in your vacuum chamber and said, no, I'll reprogram the valves and I will substitute a I will substitute for gallium a molecule of indium. Okay? So for every X moles of gallium, I will inject 1 minus X moles of indium, and then 1 mole of arsenic. I let them all react and deposit crystal layers. So I get a ternary compound, which is defined by the mole fraction X. Right? Next thing you got to do is, when you've grown the wafer of that material, find out what is the energy gap. Well, you would have had 30 years ago two different PhDs working on this. One would be working on the theory end, and one on the experimental end, building the vacuum chamber rig, writing the program for all of the valves, and then taking the wafers out and measuring the wavelength of luminescence. To do that, you use flash photolysis. That's one possibility. That means you get a very, very bright light, and you flash it for less than a microsecond, and then you have a spectrum analyzer with a photodetector and measure. After the flash occurs, the semiconductor will find itself in an excited state. The electrons will relax back down through the energy gap and emit light, which you measure within a microsecond of having created the flash. So that's called flash photolysis. That would be one way for experimentally verifying your theory. Your theoretical energy gap would come from molecular orbital analysis and quantum mechanics and working out what you expect the gap to be as well. And one would verify the other. Now, the person doing this experiment would have to change X every night, keep changing X, make a wafer, and step it up by 1% and make another wafer, step X up by 1%, make 100 different wafers. Flash photolysis on every one of them, and you end up with a table with 100 components of data, which you associate with a particular alloy mix. Somebody else might be working on the quaternaries, working on their PhD, but they're getting the hard end, because if you have 100 percentage steps of X, you would also have 100 percentage steps of Y in a quaternary, because there's 4 compounds, and you can substitute arsenic for phosphorus and vice versa, because they're both group 5. So there's 100 steps there, and 100. This person has got to measure 10,000 wafers and make 10,000 wafers. However, it might be fair enough, because they're probably coming a few years after this person, who has already set up the rig for them and learned all the earlier bits, and they're mass producing everything by this stage. Anyway, the end result is an awful lot of data, and the question is, how are you going to use it? And that's where the alloy map comes in. Okay? Because when you play around with X and Y, you're squeezing the atoms in the crystal apart and changing the lattice parameter. So the lattice parameter here on this axis corresponds to the XY mix. All right? And as you change it and you measure the wavelength and calculate the energy gap from the wavelength, then from your flash photolysis experiment, you get something like this. Here's gallium arsenide. It's just a dot in this map. Indium arsenide is another dot. The 4 binary possibilities are 4 dots. If you have gallium phosphide and you start removing the gallium and replace it with indium, you'll be moving along this line. And the X is getting bigger and bigger and bigger until you reach, you've completely substituted all the gallium for indium. So we've arrived at the single dot indium phosphide. And you can do that along all the 4 sides of this map. So the sides of that map correspond to the ternary mixes, the different values of X. Then, what about this person with the 10,000 points? Well, what you can do is you can substitute gallium for indium, and at the same time substitute arsenic and phosphorus, and you move along a line in here. So inside the map corresponds to quaternaries. And there'll be 10,000 points there, 100 between there and there, 100, 100, and 100. That's our alloy map. It compresses all of the band gap engineering information for us. And remember the end goal now, and this would be If I had been in charge of that last experiment, I would then take on the next PhD and say, now your job is to go to the wavelength axis for your thesis and work out a comb of 100 wavelengths in the C band of the optical fiber, all separated equally by 50 gigahertz in the optical frequency, say. Work out their wavelengths, and from that, work out what are the XY values, and go away and grow 100 wafers. Dice it up into chips, and we will then have 100 lasers which can transmit dense WDM, dense wavelength division multiplexed channels down our optical fiber. Okay? And that's exactly what has been done. So, in order to utilize the photonic material, now that we've selected it, we're going to make a PN diode. So we've just discussed how you use dopants to create an N and a P layer. So if this was gallium arsenide, there will be a junction there which we would refer to as a homo junction. And the reason for that is it's the same gallium arsenide that side as this side. Right? The binary fundamental material. We've just used a different dopant, tin and germanium. If, however, we grew gallium indium arsenide here and gallium indium arsenide here, but use a different value of X either side, we've got a junction between two different metals, two different semiconductor alloys, rather. And that is called a heterojunction. Okay? There's a different energy gap each side of the junction. That turns out to be very useful. The simple diode illustrated here, I've turned it on its side. As you grow it, you would have grown one layer on the bottom, an N, and then on top of that another layer of P-type, and diced it up, and I've just turned it around so that we can compare with the energy gap, energy diagram. The light would therefore be coming out here, which is the top, so that's a surface emitting LED. It's a primitive type of LED. It would be used nowadays for display purposes and whatever, but not for telecommunications. We'll see why soon. So here's the energy band diagram, P side and N side. We inject a current of electrons, a current of holes from this side, they recombine, and we get light out. Turns out only the light going out one side is useful. Up through the light through the surface. Light that goes down into the wafer and the substrate is lost. The energy gap corresponds to the center of the LED spectrum. There it's shown. There are other energy possibilities in this that are not shown, however. There are some of the electrons reside a little bit further up. They don't fall down into the bottom of the basin because the bottom of the basin levels might be already filled. So there are some electrons further up. In fact, the spread of energies in the band is kT. K is Boltzmann's constant, and T is 300 Kelvin, room temperature. So there's higher energies, and when they relax back, you get shorter wavelengths. Also, there are energy levels within the gap due to the dopants, the acceptor and donor levels. That's a smaller gap. That smaller gap means longer wavelengths. So the LED spectrum is much broader than we expected. That's a problem, because in telecommunications, it's not a problem for illumination purposes. But for telecoms, we don't want a spread of wavelengths or we'll get chromatic dispersion. We talked about that in part 1 of our text. So we would prefer a much narrower spectrum, and that's why we need to progress to a laser. Before we do that, we can make an immediate improvement to the LED. Okay. The next improvement which occurred was the edge-emitting LED, illustrated here. There's a lot more processing involved when you're growing your wafer. You start off and you take a wafer that you'd grown some other day, cooked it elsewhere, and you'd start off with a wafer of just gallium arsenide. Put it into the chamber, and then start injecting the gases and deposit an N layer. Okay? So you're doping with tin. And then another N layer, and another P layer, and another P layer, and you'd finish off with injecting materials which are oxidized. You oxygen to give an oxide layer. That's an insulating layer. The next thing you do, having done the wafer is taken out, and you'd bring it down to the wet bench, the wet side of your clean room, and you'd use etchant acids to etch away a dip in the oxide. So that's illustrated there. And having created a dip, you will then metallize it. Now we have a situation where when we inject current, it's forced into a stripe between the oxide regions. That's an important feature of this type of ELED. The current is confined. I've written it down here. Confinement of current by the stripe. That's this contact stripe. In fact, you'll get a sheet of current going down now. Now the next thing is, because of the way we selected these alloy mixes, that's aluminium 0.3 mole fraction, gallium 0.7 mole fraction. The energy gap for that, according to your alloy map, is 1.8 electron volts. The next layer is a mix, and it's aluminium mole fraction 0.1, gallium mole fraction 0.9. Go to your alloy map and you will find the energy gap is 1.5. And the next layer, we're back to 0.3, 0.7, same as down here. But because we have a different dopant, it has a slight effect, but not a lot. So this is 1.83 electron volts. These regions here are the heterostructures we talked about. There's a heterostructure there, and there's another one down here, because we're changing from one alloy mix to another, and then from one alloy mix to another. And in the, what's now, we will call it a double heterostructure, the filling in the sandwich has a lower energy gap. That means the carriers are confined in there. They don't want to go out to where the energy gap is bigger. That's our second confinement, carriers by the lower energy gap. Now it also turns out that that particular alloy has a slightly higher refractive index in the sandwich than the layers each side. So it's a bit like an optical fiber. The light is trapped by total internal reflection to that layer there. Bounces up and down and then emerges through this end window here. And I've tried to depict the pattern of light coming out that end window there now. It's coming out from the sandwich layer and it's oval shaped. Okay? It's a very thin window. It's only several hundreds of nanometers thick. So light going through a narrow slit diffracts up. And the narrower the slit, the more it diffracts. So as far as the light getting out is concerned, there's a wide slit in this plane and there's a narrow slit in this plane. So this light would diffract a lot into the vertical direction, but not so much into the horizontal direction. So the oval shape reverses due to diffraction. The light that has arrived out is higher in this plane than in the sideways plane. You can imagine that. There's a picture of it in the book, a drawing that you can redraw. So what happens is, by all of these wonderful methods of carrier confinement, which only came about because of our knowledge of bandgap engineering and our ability to control the chemical vapor deposition processes very, very carefully, we end up with this performance improvement that I want to explain. The surface emitter on the last slide has an irradiance of about 200. This one is 5, 6, 7, 8 times better. Now, what are the units? How do we compare them? Well, how many watts of light can we get out of either diode, the surface emitter or the edge emitter? The number of watts from every square centimeter of lit surface. So that's the lit surface there. You work out the number of square centimeters. That'll tell you how intense the light is concentrated in this lit window. But not only do you want that, you want the light to be launched, not to diffract all over the place, you want it to be launched into a narrow cone, as narrow cone as possible, so that you can use a lens to focus it down either to a tiny optical fiber, as in that picture there, or to a compact disc, where you want to focus it down to a tiny spot and write data or read data. So the smaller this spot size and the better that quantity there is, the more light you can focus down into a tiny spot for communications or for storage of data. And the whole thing is based around the concept of the double heterostructure. Now, we will evolve that structure as shown there into a laser and use the same concept, but with a few added items that you need for laser action. And that's what we need to address next. The double heterostructure laser is the workhorse of modern telecommunications systems around the world. So let's start talking about the lasers at this stage. Everybody knows the acronym, light amplification by stimulated emission of radiation. What really happens with a laser is light, a light field, interacts with a system of molecules, or semiconductor crystal. And what we would like to happen is stimulated emission to occur whereby a photon of light inside in the sandwich of the double heterostructure stimulates an electron in the upper conduction band to recombine in a vertical transition to the lower band, to the valence band, and emit another photon. So if 1 brings 2, before we get to the end of the laser, the 2 makes 4, the 4 makes 8, we can see that's an exponential increase. The trouble is, that photon, and we're going to show in a minute, Einstein showed, and it doesn't, not very easy, not hard to show, we'll do it in a minute. He showed that it's equally likely that this fella will stimulate absorption, right, and become absorbed. And the only way you can make sure there's more stimulated emission than stimulated absorption is to ensure there's more population, bigger population up here. N2 must be bigger than N1, which we call population inversion. So now we've got amplification by stimulated emission. We had to pump the system. When the students were doing the alloy map, what they did, I said you could use flash photolysis. Right? That's the way, that was one way of pumping the upper state. So by bright flash of light, the light is absorbed, the electrons end up in the upper state, and you invert the population. However, there's one letter missing from LASER, and I'm going to ask you, can you guess what it is? Because as that stands, we would call that a semiconductor laser amplifier, or a semiconductor optical amplifier. It's not quite a laser yet. To make it into a laser, we must make the amplifier into an oscillator. How do you make an amplifier into an oscillator in conventional electronics? Yeah. Feedback. So we need some kind of feedback here. And in the case of an optical oscillator, that means a mirror. We need a mirror at each end. So the letter I would say that's missing is O, oscillator. You could make it into a O apostrophe laser if you wanted to. There it is, O apostrophe. Anyway, or whatever you want to do. We need two mirrors. Luckily, the crystal people are good at that as well. Because when you put a tiny scratch on the end of, you can saw the wafer into long stripes, and then you put a little tiny scratch, and you can cleave it into chips. So the sides might be sawn, but the end parts of the chip would be cleaved, and they end up like crystal mirrors. Okay? And that's how we produce our oscillator. So here's the light, partly reflected back down. The length of the oscillator is L. The light keeps reflecting up and down. Standing waves build up in this in such a way that an integer number of half wavelengths of the light equals L. So here we see there is a way here of partially controlling the wavelength of the light as well as the band gap engineering. When we then pump it sufficiently, we'll suddenly see a change in the emission pattern. Spontaneous emission, unfortunately, is omnidirectional. It's equal in all directions. As much light went down into the substrate as came up to the window. But once we get this thing oscillating like a laser with sufficient pumping and sufficient feedback, immediately the spectrum narrows, the intensity rises, and within the spectrum we can see fine detail. There's a transverse mode associated with the sideways dimensions, and there's these longitudinal modes here, n lambda over 2 equal to L, within that. So a very fine spectrometer would show that within the transverse mode pattern there is fine detail, fine structure associated with the longitudinal modes. All right, well, there's a number of lessons that needed to be learned in order to make all of this work. And Einstein gave the clues, as always. This is quite straightforward. Einstein took what was well known from Boltzmann. The population in a system of molecules at temperature T, where there was an energy gap between the levels delta E. Okay? The population exponentially changes with the energy gap. That was Boltzmann's contribution. And as the energy gap gets bigger and bigger and bigger, you will get less and less molecules in the upper state. That's called thermal equilibrium. Now there was another useful expression around given by Planck. Planck showed that when you heat up a body, it emits photons. And the spectrum of that emission is given by his expression. The density of light at any particular frequency, that's the optical frequency, okay, depends exponentially, looks a bit like Boltzmann. It's got the E to the energy gap, HF, okay, over KT, and there's a -1. So this is called Planck's black body radiation formula. High black body, well, if it's not black, the surface will discriminate against some colors. Right? So if we make it black, it'll be uniform across the spectrum, and it'll give us the true optical density of light across the whole spectrum. So from that, you can see, as the temperature gets higher and higher, the object gets red hot, then it gets yellow hot, and then it moves into the blues, and then into the ultraviolets, and when all the visible colors are being emitted, it's white hot. And that's what every blacksmith knows when he's using his forge. So Einstein said these two have to be related. If light is going to interact with molecules in an amplifier, these two have to be related. And this is how he related them. And that gives us the clues about how to make the laser work. Okay? Einstein said that you could have spontaneous emission going down the way. You can have stimulated emission, electrons going down the way to the lower level. but you can also have stimulated absorption, electrons going up the way. He said what goes down must equal what comes up in order to have an equilibrium situation. Right? So some coefficient from 2 down to 1 times the population up there, that's N2, plus some other coefficient from 2 down to 1 times the population up there, also multiplied by the stimulating photon density. This is a stimulated term. That must equal what's going the other way. A different coefficient from lower state up to the higher state, multiplied by the population down there that's capable of making the transition. It's a stimulated process, so you again multiplied by the density of photons at that frequency corresponding to that gap. So that's our dynamic equilibrium, and that is Einstein's contribution. It was simply a matter of making that fit with the other two equations, Boltzmann and Planck, and you had the clues. So you can quickly rearrange that, and you will see, just bring a couple of things across, and you'll get rho of F equals this expression. And that has to agree with Planck. All right? While you're doing it, there's an N1 over N2 in there, so substitute in Boltzmann. So sub in Boltzmann into Einstein, rearrange it, you get an equation that must be the same as Planck. So stand back and look at it, say, how do I make them agree? And you can see straight away, the coefficient in here is 1, unity. The coefficient in here is B12 over B21. Therefore, the B's are equal. That's the first conclusion Einstein drew. The coefficient for stimulated emission is identical to the coefficient for stimulated absorption. That is why you have to have population inversion. You have to reach a threshold pump level, at which stage the upper population is bigger, and then there's a possibility of laser action. That's lesson number 1. Lesson number 2 is equally important. To make this expression identical to Planck, look at the rest of it, and you will see that all of this jumble of stuff out here, right? It's 8 pi h, it's constants except for the frequency cubed. All right? That must be equal to spontaneous to stimulated, A over B. Now, why is that important? Important because we don't want spontaneous. We want to get rid of the A process as much as possible, and we want to enhance the B process. Okay? And you can see it's all dependent on F. All the rest is a constant. Okay? So if you take a frequency, the one we're looking for, infrared 10 to the 14 hertz, middle of the C band, it's 2 by 10 to the 14, but make it easier for you. Put in 10 to the 14 into that expression, and you'll find it comes out at something like, into this, where are we? Yeah, it comes out at about 100,000. The likelihood of spontaneous at infrared or visible frequencies is 100,000 to 1 against. It's going to be always spontaneous. Very difficult to get stimulated emission. On the other hand, put in FM 100 megahertz radio frequency. Put 10 to the 8 into that expression, and you will get the exponential will give you a 1, but then you've got to subtract another 1 there from that. 1 minus 1 is not. That's an important thing to remember when you're reading it in the book. So the ratio is 0. All right? That means there's no spontaneous, it's all coherent emission. So it's very easy to make a radio frequency coherent transmitter. That's what Hertz had done a couple of decades before Einstein. You just put an oscillating current into a dipole and you get your coherent emission. But you try it at optical frequencies and the laws of physics are 100,000 against you. And for that reason, Einstein gave all the clues. Laboratories around the world set about trying to build a laser, but it took them several decades. Long after he had passed. One way or the other, we've got to pump the molecular system up to a threshold. So a couple of decades after Einstein, main man succeeded in achieving the goal to get an optical oscillator that lased. Got a really pure ruby crystal, an artificially grown ruby crystal, because natural ones tend to have imperfections in them, and it'll be like an optical fiber; it'll quickly absorb everything, all those bits of unwanted material. So a ruby crystal, and then a really bright light, like the one we were talking about for flash photolysis, a really bright shock of light, and then mirrors at each end. And I can tell you it was one heck of a problem to line up those mirrors so they were precisely facing one another. So Mayman's laser was about this size, 2 mirrors, a ruby crystal, a big huge ultraviolet lamp, and ellipsoid mirrors to focus it all down right onto the crystal. Give it an almighty flash for a microsecond and hope that you can get a deep red pulse of light out the end mirrors. As I said, today we could line up, Laura could line up those mirrors, no problem, because she would use a laser, a helium neon laser, or even this pointer laser. Okay? You could just take the reflections from the 2 lasers, 2 mirrors, onto a photodiode and look at the interference pattern. And when you had the interference pattern perfect, you'd know that they were perfectly parallel. But they didn't have lasers. Mayman didn't have lasers. So it was a very, very tricky process, that alone. Anyway, in the late 50s, early 60s, they achieved it. And then they moved on. They says now we want gas lasers, and we want liquid lasers, but most of all, we want semiconductor lasers. And that's what we've been talking about. The question is, how do we turn that LED into a laser? And we found we can cleave these end mirrors in the crystal. I've simplified the diagram now. This is probably a double heterostructure. All right, so there's many, many layers. But for the purposes of looking at how do we get to the pump threshold, we'll simplify it. There's the window that we had, the oval, a while ago. Okay? And on a power against current diagram, when we reach threshold, the power shoots up rapidly. LED turns to laser action. That current there is the threshold. We need to know what it is. You'll find it very quickly. Because all you've got to say is that the power inside the crystal reflects partly, that's R. R times the power, Pi is the power incident. It must build up, we said exponentially. 1 photon gives 2, gives 4, gives 8, that's exponential. Builds up, and by the time we reach this end, Z equal to 0 or Z equal to L, the power must have come back to its original value. So we say unity round trip gain tells us Pi must be equal to the reflected Pi times the exponential gain until we get to length L. So that's a very straightforward equation. It's just a log equation. You cross out the Pi's, twist it round, and say, look, I can make a very reasonable assumption here. The current going into the device is producing gain. More current, more gain. So make them proportional, and we get an expression in 2 or 3 lines for the threshold current. Right, that's done in the book, and you can verify it yourselves. It's very easy, but I just want to look at the form of it. The threshold depends on the width, W, by the length. That makes sense. It's the area of the stripe. If you have a bigger stripe area, you're going to need more electrons to pump what's underneath it, pump it to a higher state. Next, alpha is the loss. That's the losses per centimeter. So the light going up and down are losing power at a rate alpha per centimeter. Okay? And then they're also losing light at the end of the chip. There's a reflectivity R. This loss is distributed along the whole length of the chip. But the reflectivity is not. It's abrupt at each end. So to combine them, we divide by L. So that expression there is effectively saying the abrupt loss distributed over the length L, added to the other losses per centimetre, gives us the amount of pumping we have to do. The pump is making up for the losses. And that's the form of that expression there. Okay, that's the steady state behavior of the device. The power is made up of photons, so you can draw that diagram slightly differently. They're all straight out of the book. Well, I forgot to say, by the way, when you wanted to work out the reflectivity, you go to Fresnel's equation from fundamental optics. N1 minus N2 to be squared over N plus N2 to be squared. Right? N1 is the index inside. It's 3.6 for gallium arsenide. N2 is the index outside air, so it's 1. So it's 3.6 minus 1 to be squared over 3.6 plus 1 to be squared. That's Fresnel's equation. It's the same as the equation you have in your electrical circuit theory, where you have an impedance Z1 and you arrive at an impedance Z2 and you get a transmission and a reflection. Same form expression. If you think back to the Z1, Z2 equations, they look just like that. Now, that gives us, it turns out it's just the kind of number we want. Do it yourselves with your calculator, you see it's about 32%. So over 60% of the light is emitted at this end, and it's identical at the other end. So our laser has two outputs. We would focus one of them using a microscopic lens into the fiber. That's a job in itself, positioning the microscopic lens exactly correctly and then connecting the fiber up exactly to the focus. And to automate that process is another mechanical engineering. It was a nightmare, but it's done in an automated fashion today. The other output, you can make great use of it too in engineering. You can focus it onto a photodiode. Okay, for example, you can use it as a monitor. If the laser dies, you're in a telephone exchange, you have an array of 100 of these for WDM, say, and one of the 100 goes down, the photodiode sets off an alarm. Okay? And the whole system is programmed that all the internet packet data are rerouted to another one of the WDM channels, while the engineer is getting at this transmitter to identify what the problem is or replace it. So there's no downtime when these things happen. They can happen very easily because these diodes are extremely sensitive. If a sudden pulse occurs due to somebody, I would say an interruption in power supply, when you get a power supply interruption, you get a sudden surge of current in both directions. That surge is enough to give a surge of drive current that the intensity of light at the facet is higher than that on the surface of the sun. That can easily happen, and you just burn a hole in the laser chip, it's dead. So you must always have very carefully controlled current drivers driving these lasers. You must be monitoring them all the time. You must make sure there's never any surges of any kind, or they're all dead. That diagram, last one, can be written slightly differently. You can, instead of power in milliwatts, you could write photons, the photon density per cubic centimeter of space against current. All right? Now, the photons in the cavity, there they are, n, say, n is the number of carriers, is changing with time. Right? dn dt. Why? Because you're pumping it with bias current IB. To turn current into electrons, you just divide by the electronic charge. Right? Then you get electrons per second instead of amps. And if you divide it again by the volume of the active layer, right, you'll get the current density. So the current density is changing with time as you pump it with this current. Meantime, everything is deactivating by stimulated emission and by spontaneous. the stimulated emission depends on both the photons S and the carriers N. So there's a product there times some coefficient B. And they're also de-evac. The the carriers have an average lifetime tau before they deactivate spontaneously. So the rate is 1 over tau times N. So that's our differential equation for the carriers. And you can write a similar equation here for the photons. There's a common term. Stimulated emission lost. Well, that's stimulated emission gained as far as photons are concerned. Photons are being generated at that rate by laser action. Okay. Also, the spontaneous action is contributing to the photons. But remember, spontaneous is all over the place. It's random. That means it's omnidirectional. And only a tiny fraction, less than 1%, of those contribute to the output light. The rest of it goes out to the edges of the laser where it's absorbed and all over the place. And then finally, the photons, ds by dt, they're being lost with time according to the average photon lifetime, Tp. So the carrier's average lifetime is tau, and the photon's average lifetime in the cavity is Tp, the photon lifetime. Equations look very similar. They're coupled differential equations. You've seen them all over the place. You've seen them in your mechanics in first or second year. You've seen them in your circuit theory with LCR circuits. It's the same kind of differential coupled equations all the time, LCR circuits. The common term is the BNS that couples N to S. To solve them, you can ignore the middle term there for spontaneous. We said it's very small. That makes life easier. Then you have two conditions. My pointer laser here is said to be CW. Right? It's obviously continuous wave. It's a DC light beam. All right? If you have CW light beam, ds dt is 0. So that's the first condition. Just stick that into the S equation and you get the threshold current density. There it is. It's a very simple expression. N threshold is 1 over P photon lifetime. The other condition is also straightforward. Okay? And that once you go above threshold, right, as many carriers are being created as are disappearing. There's a dynamic equilibrium. Otherwise, the chip will blow up. It will become too positive or too negative in different parts and it will just explode. So, above threshold, dN dt is 0, and you can put that into the other expression along with our N threshold, and you get an equation for the light. And that equation is just what we expected, because look, it has the form of a straight line. Y equal to mx plus c. Examine that, and you see it has the same form. M is the slope, and c is the intercept. So if you just measure this like characteristic curve, right? We use a power meter, and then convert to photons using Planck's law. Okay. So use a power meter to measure the PI graph, convert it to an SI graph, and then from the intercept and from the slope, you can look at them. One of them contains tau, and the other contains Tp. So you can find out the carrier lifetime and the photon lifetime in your laser from that experiment. They're very important because those parameters turn up all over the place as you play around with different aspects of the lasers. You'll find the photons live for a couple of picoseconds before they're emitted. The carriers live for a couple of nanoseconds, 1,000 times longer. Now, this graph also shows you that in use, you would bias the laser, IB, well above threshold, IT, there it is, okay? And you would get an average power out or photon density out. And then you'd modulate it with your data bits, your ones and your noughts, and you'd get an optical signal out like this. That's what we're trying to illustrate there. If for any reason, when you're biasing it like that, the threshold changes, it can severely affect your transmission system and cause errors all over the network. For example, if the threshold move up the way, all right, that knee would intercept this data signal, right? And you start clipping the bottom parts of the data signal, same as diodes are used for clipping things in electrical circuits. Right? On the other hand, if it moved the other way, the threshold, and it can, the whole bias point moves way, way up, and you can move up into non-linear regions of the curve. That's actually very important. When you connect a laser to an optical fiber, you're putting another window in front of the chip, because the fiber has got a window, a cleaved facet itself, and therefore it'll reflect maybe 5–10% of the light. And if that's reflected back into the chip, go back to your threshold equation, and you'll find there's an R in it. You've effectively changed the reflectivity in the threshold equation. Right? If you increase the reflectivity due to feedback from an optical fiber, the threshold goes down. And when the threshold goes down, the whole curve moves down, and you're modulating on a higher, different part, perhaps a non-linear part of the graph. So we must be very careful in these systems about back reflections of any kind. I'm going to move on. I'll finish on this one. Now, quantum well lasers are becoming widespread. In the old days, it was the domain just of physicists, but these are widespread now and moving into all areas of optical systems. So what's this all about? This is where my Bower-on experiment comes in. Okay? I've again turned the PN diode chip on its side. Okay? We have the P layer, which is grown on top of a thin layer, and then that's grown on top of the other N layer of the chip. If this middle layer, which we're going to call the active one, is made thinner and thinner and thinner, you arrive at a quantum well device. Now, to make it thinner, it means you need to be able to grow in the deposition chamber layers of material which are only about 20 nanometers thick, 200 angstroms. So that's pushing deposition technology from the crystal growers and all that to its limits. But it can be done today. We can't do it with the old-fashioned chemical vapor apparatus that I've talked about already. You need to use something like metal organic vapor phase deposition, MOVPE they call it, or molecular beams. You inject molecular beams onto the surface of the crystal. That's molecular beam epitaxy. So these new machines are able to grow nano layers that are required for this purpose. And we're going to show that when the inner active nano layer of this laser is narrow enough, the threshold drops dramatically. And there are several reasons we need something like that. The higher the threshold, the more heating that takes place in the background in the chip. Heat degrades the behavior of the thing, and it broadens the spectrum. That adds to chromatic dispersion. All kinds of problems arise. Heat can also, as we've seen, kill the chip if there's a surge on top of this heating. So there's many, many reasons why we want a low threshold. Another one is for optical computers, which a lot of work is going on them today. If you have a very, very low threshold, instead of tens of milliamps, if you had tenths of milliamps or lower, inside your computer you could have thousands and millions of these lasers talking to one another optically, and the currents are so low that you can actually manipulate data with AND gates and NAND gates and adders and subtractors and whatever you want. So you have the basis of a photonic computing. Low threshold can get us to that stage. And that is a target which is very interesting for supercomputing. Okay, let's look at this, this process then. So we've learned to grow a very thin LZ layer. Notice, by the way, I've turned the chip on its side. So Z is the growth direction. You're depositing these active layers, and then you're depositing the cladding layers. So if we can achieve this, what happens is the electron waves are trapped, just like the waves on our boron, and only the lowest electron modes are oscillating. So there's the n equal to 1 quantized level up in the upper conduction band. And here's the next quantized. This is our ring on the boron, our inner optical fiber. But in the this laser, it's actually a line of a wave and another trough on a node and another line. It's linear geometry instead of circular. But nevertheless, these are the quantized electron oscillating waves. And in the whole band, we also have these oscillating permitted standing waves. And just like in our waves in our laser oscillator, an integer number of these must fit within the thickness Lz. So n, an integer of half wavelength, now this is now the wavelength of the electron, not of the light, must make up the thickness of the active layer. That sets the quantization condition, that integer n. Okay, because that must agree with these other equations. The momentum is h over the wavelength, Bert de Broglie, okay, and the energy is p squared over 2n. Once again, you can in a line you can combine those three. Combine the three of them to get the energy, right? Substitute one into the other, then put n equal to 1 and then n equal to 2 and subtract, and you'll get the energy gap. All right. Combine them, then take the integer 1, the integer 2, subtract, and we've got the gap here between the valence and the conduction band. So that's the energy gap. I'm using a little g. That's the energy gap in the active region. Now out here, we have a much wider energy gap out in the cladding. That's another thing which helps to confine all the particles that are participating. Okay, we now just use this energy gap expression to compare bulk, I'm going to call it bulk semiconductor, with our new novel quantum well crystal. This is our quantum well crystal. And if you put an LZ value for a bulk material in there, you'll find that the energy gap between the quantized levels is only about a fraction of a milli electron volt. But if you put 20 angstroms, 20 nanometers in here, the energy gap of the quantized levels is bigger than the thermal distribution, kT. And if it's close to or bigger than kT, there's only 1 or 2 energy levels occupied by the electrons in the upper or lower band. And if that's all there are, that means you can excite inversion much more easily, and the threshold current shoots down. So our quantum well laser gives us a threshold, I'm saying, decades lower. Now it is a tiny active region, so the power is going to go down as well. So what we do is, after the cladding, we grow another active layer, and then another cladding, and another active, and we grow a stack. And that's an MQW, a multiple quantum well laser. And then the output from all of them combines to give you plenty of power. They've even reproduced this process by confining, as well as confining in the Z direction, you can confine in a second direction in 2 dimensions, and then instead of a quantum well laser, you'll end up with a quantum wire. And you can confine it in 3 dimensions, and you end up with a quantum dot laser. And these are all steps towards getting the tiniest threshold so that we can build these photonic computers. However, it's nothing abnormal today to see these kind of devices, and they are moving their way into telecommunication communication systems as we speak. So I'll leave it at that. Thanks very much. Thanks, Laura.
Maybe you have time for a couple
No,
of
yeah.